In the last two sessions, we saw how to use nonlinear data structures like binary search tree, AVL trees and 2,4 trees to perform the search operation. We saw that in binary search tree, the performance in worst case is not so efficient, and so we added height balancing properties and size properties, so that the height of the tree becomes bounded by logarithmic of n, and so all the operations, that is query and the update operations, take place in order log n time. The question is, can we develop a procedure which is faster than logarithmic time procedures? So, is it possible to develop or design a search algorithm with running time which is of order 1 or which is constant? The immediate answer we know comes from arrays. We know arrays, there is a direct access. So, one can directly access any cell that is needed to be accessed, unlike list where the access is sequential. In array, cell number 10 can be directly accessed by for retrieving the information. So, we are going to try to use this structure of arrays, advantages of arrays, and try to develop a procedure which is going to be much faster than hash table the search trees. So, let us look at an example where we have a sequence of numbers and they are stored in an array. To make things simple, we also assume that the sequence is already sorted sequence, that is, sequence is in increasing order. Now, let us try to find a particular key in this sequence, which is say 44. Now, we know that since the sequence is started, we can sequence is sorted, we can make use of binary search, which will find the key in logarithmic time. You know, if there are n keys in a sorted sequence, binary search takes order log n time. If we do a sequential search, we know it will take us linear time in the worst case. So, if you have a sorted sequence, then we know search can be done in logarithmic time. Question is whether we can still do faster than that. Now, we know that in array we have a direct access. So, making use of this key idea, if 44 or the key that we are trying to search is stored in A44, the search would be done in one step, right. So, what we mean is, if you have a array which is long, which is big enough, and so this is my array A and this is my 44th location, this is A44, and if I store 44 here, then your access will take only one step or will be achieved in constant time. So, if we have ample storage available, one can use arrays to retrieve information in constant time or in exactly one step. The key idea is, if you want to retrieve, if you want to store k, store it at the kth location in the array which is going to store your keys. So, when you want to access or you want to search for k, you have to just go to a k. If a k has the value k there stored, then your search is successful, otherwise it is unsuccessful. There are obvious disadvantages with this procedure. We will see them as we go ahead. Immediately we can see that if the keys are too large, then we are going to require a lot of storage space to achieve this constant time complexity. One can overcome this problem of storage space by using what are called hash tables. So, hash tables are basically based on arrays. Only thing is the array is proportional to the number of keys that you are going to use. So, the size of an array will be proportional to the number of keys that we are going to use. And instead of keys themselves being as an array index, the key is going to be used to compute the array index. So, hash tables are going to be based on arrays, we will use the efficient access of arrays and try to do the search in time which is less than logarithmic time or time which is nearly constant. This idea of storing key k at a array index k are called direct address hash tables. So, if you use the key directly as the array index, what we get are what are called direct address hash tables. In this, each slot or position corresponds to a key in U. U is the universe of the keys that we are going to deal with. So, it is a large universe from which the keys are going to be drawn. If there is an element x with key, then Tk contains a pointer to x, otherwise Tk is empty, represented by a nil. So, a direct address hash table is going to be, so this is U, the universe of keys from which we are going to draw our keys. K represents the actual keys that we are going to work with in the present application, and in a direct address scheme or a direct address hash tables, each, so this is T is your direct address hash table, each slot or position corresponds to a key in U. So, if I have a million keys in U, then I will have a table having million cells in it. The size of T is exactly equal to size of U, and each element k of k, Tk will contain a pointer to that element. So, we have a pointer to this particular element. So, 2, if I look at 2, it is going to be at the second slot in my table 2. Similarly, if I am looking at 8, it is going to be at 8th slot in my table. This is exactly as what we saw earlier, is 44 is stored at A44. Similarly, here for every key in K, you have a slot blocked for it in the table T. Otherwise, if the key is not present in K, then that slot is going to be free. Number of slots is equal to or depends upon the universe of the keys that you are looking at. If you look at the performance of the direct address table scheme, we see that access is very fast, addition and deletions are also very fast. We simply have to go to, if I want to store say 112, I just have to go to the 112th location in my array A or my table T and store 112 there. Similarly, the delete operation is also done in one step. Search also is very fast. If you want to search for a key, simply go to a table whose index is that key. If that slot is nil, then the key is not present. If the slot has the key, then the search is going to be successful. So, this particular scheme of storing data, that is why using direct address table is extremely efficient in terms of performance. Though it is efficient in performance, it is bad in storage. If the universe U is very large, then the size of T is going to be extremely large, and the set k of keys that you actually want to store can be relatively small with respect to u, so that most of the space allocated for the table is vested, right. So, let us try to illustrate this particular point. Now, suppose if you want to save keys like this, some arbitrary, I have written some arbitrary keys. So, I have only 3 keys that I want to store, but if I look at my size u, then it is going to be extremely large, correct. My size of u, correct, which is the universe of all keys, is going to decide the size of the table. Now, in my u, you also going to have a key like this. That means, your table T, which is going to store the actual keys, should have this many cells or this many slots, out of which only 3 slots are going to be used. You want to store, so the number of keys that you want to store actually, which is represented by k, in this case is only 3, whereas u is extremely large. So, to store such things and to want and to have a fast access, you need a table. Right. So, I need a table whose size is going to be equal to this. So, access, add, delete are all going to be fast, but extremely inefficient in terms of memory. It also is going to waste lot of memory, because most of the slots in your table are going to be empty and so are going to be wasted. So, though hash tables, direct address hash tables are very efficient in performance, they are extremely inefficient in memory management. So, hash functions are used to overcome this inefficiency of storage management. In direct addressing, we saw that key is used as a index to the slot where it is going to be stored. In hashing, we use what is called a hash function. So, the key is used to compute the index where the key is going to be stored. That function is called a hash function. So, given a key k, hash function computes hk, and hk is going to be the slot in the table where key is going to be stored. So, hash function is from the universe u of keys to a bounded set from 0 to m minus 1, such that every key in universe is mapped to some number between 0 to m minus 1. We say that hk is the hash value of k, or we also say that k is hashed to hk. The aim of this hash function is to reduce the range of indices that needs to be handled. So, for example, in the example which we had written down to show that direct address table is inefficient, if there was a way of mapping those 3 large keys to keys which are very small, then the requirement on T would have not been as large as the set U. So, idea is to reduce range of indices that needs to be handled, or where your keys are going to be mapped. Now, there are many ways of, there are many popular hash functions, out of which a division method is one of the very popular functions. Hash functions are also called compression maps, because they try to compress the range of the indices. Now, any hash function that you are going to deal with certain values of m are going to be good and certain values of m are not going to be so good. Usually m a prime which is not near to any powers of 2 is a good choice. So, in division method when h k is equal to k mod m, so that means you are looking at all the keys modulo a number m. We know that once you do modulo m, all your keys are going to be mapped from 0 to m minus 1. Correct? For example, in the first example that we looked at, in this example, if you take your m to be say 7, I know 7 is a prime number. 7 is not such a good because 7 is very near to 8, which is 2 cube. 11 probably is a better choice, but anyway let us try to work with 7. Then this is going to be mapped to. So, now all your keys you are going to do operation modulo m, that is you will divide by 7 and look at what is the remainder. So, as you divide 11 by 7 your remainder is 4. So, this is mapped to 4. So, if this is my key h k is going to be 4. If this is 22, this is going to be mapped to 1. This is going to be mapped to 0 and so forth. Correct? So, when you are doing modulo m, what you are looking at is you are dividing the number by m and looking at the remainder. So, remainder we know as you divide by m is going to vary from 0 to m minus 1. So, one of the popular hash functions is the what is called a division method or the modulo function, in which typically m is chosen as a prime which is not near to a power of 2. Another popular compression map is called a MAD method, which is you use all the functions multiply, add and divide. So, h k is mapped to a k plus b modulo n, where n is a prime number and a and b are chosen randomly such that a modulo n is not equal to 0. This function is chosen in order to eliminate repeated patterns in the keys that we are going to deal with. So, these are the popular hash functions that are used, the division method and the MAD method. The immediate problem with hash functions, whether you use the division method or MAD method, is going to be if my m is small with respect to the number of keys that I am going to work with, then we are going to have collisions. Again, let us illustrate this with the first example that we are looking at. So, in this example, as we said, if you take m equal to 7 as we were looking at, and the number of keys that we have here is 1, 2, 3, 4, 5. The number of keys stored here are 12. Now, the possible values to which these 12 keys can be mapped is only 0 to 6, correct. For example, so if I look at u is the set of all keys that I am dealing with here. I know the size of u is 12. So, if I look at my hash function as modulo 7, so your h from u has to be from 0 to 6. So, h has to be from 0 to 6. Now, there are 12 keys which are going to be mapped to 6 keys. So, definitely there are going to be at least 2 keys which are going to be mapped to a single value. Right. For example, we saw this 28 is mapped to 0 under your scheme n mod 7. Under this scheme 28 is mapped to 0 and 77 is also going to be mapped to 0. So, if your m happens to be small than u, then there is chance that some of the keys are going to be mapped or going to be hashed to the same value in your range space. So, we say that in such a case there is a collision, that is, we saw that 28 and 77 both were mapped to 0 under the hashing scheme. We say that a collision has occurred. So, the ideal situation is you avoid collision altogether. That means, you have to choose a very wise hash function. Now, in practice this is extremely difficult to achieve. We saw that an ideal situation can be achieved by direct addressing scheme, but then direct addressing scheme is extremely inefficient in memory management or in memory requirement. If you want to avoid collision, hash functions are also such ideal hash functions are not easy to achieve. So, the key problem is to have hash function which is going to minimize the collision. That is, the chances that two keys are going to collide is extremely small. So, what we are going to try to do is look at such hash functions, that is, functions where possibility of collision is minimum. One way of resolving collision is what is called chaining. There are different ways of resolving collision. As we said, one is to try to achieve or try to get a function which will minimize collision. Once you get them, then you need still schemes to resolve collision. One popular scheme is what is called collision resolving by chaining. In chaining, we put all the elements that hash to same slot in a linked list. So, at each slot we create a linked list, and if a key is mapped to this particular slot, it is inserted into this linked list which is stored at that particular slot. So, your slot jth slot will contain a pointer to the head of the list of all stored elements that hash to j. So, your table will still have m slots, which is 0 to m minus 1. At each slot will have a pointer which will head to the list of all stored elements that hash to that slot. Again, if there are no such elements, your slot j contains a nil node or a null node. So, this is an example of a hash table where collision is resolved using chaining. So, we see that in my k. So, if you look at k 1 and k 4, their hash values are being mapped to the same slot. This just means that under your hash function h k 1 is equal to h k 4. This will mean h k 5 equal to h k 2 equal to h k 7. When you have a keys being hashed to the same slot, we create a linked list at that slot and insert this element into that linked list. So, k 1 is going to be scanned first. You see that its value, if I call this as 0, this is 1, it is mapped to 1, then you insert it at the linked list. Then as you go to k 4, you see that that is also hash to value 0 or hash to value 1. So, we insert k 4 into that linked list. So, we create such a linked list. So, this is called collision handling using chaining. So, in the chaining we use the slots, and at each slot we maintain a linked list. This linked list contains all or holds all elements which are hashed to this slot. Let us try to analyze the performance of hash tables where collision is resolved using chaining. So, obviously, the worst case is all the elements that you want to store gets hashed to the same slot. Like for example, if all my elements were multiples of 7 and you were doing modulo operation 7, then all elements would be mapped to the same slot, which is 0. Like for example, I am looking at keys like say 21, 28, 70, 63, 42, and I am doing operations modulo 7. Then all these keys are going to be mapped to the slot 0, and that is going to be the worst case. So, in that case, one will have to sequentially try to search the elements, or we also have to insert in this linked list. So, if you want to search for a particular key, we will go to slot 0. First, we will do modulo m, that will take us to slot 0. At slot 0, all these 5 keys are going to be stored, and that search is going to be a search in a linked list. So, it is going to be sequential search, that is going to start from head of the list and go to the tail of the list. We know such a search will take us a linear time. So, what we see is, in worst case, performance is linear in nature, which is not an improvement that we were looking forward. But a worst case scenario, we know does not happen every time. That is, it is going to be rare that we get all the keys which are multiple of a same number, and the same number is chosen as a for using the hash function. Right. For example, if we had used 11 here instead of 7, correct. So, if you do operations 11, then this would be mapped to 10, this would be mapped to 6, this would be mapped to 4, this would be mapped to 8, and this will be mapped to 9, correct. So, instead of 7, if we would have used modulo 9 operations, then we see that all the keys in fact are mapped to different values, or they get hashed to different slots. So, worst case, we know in practice is not going to be quite often. So, what we look at is what is the average performance. Best case we already seen. The best case is you have an ideal hash function, or you have what are called direct address tables. In that case, we know all operations are going to take a constant time. Right? So, worst case is linear, and best case we know is constant time. The best case are nothing but the perfect hash functions or open addressing table, that is there are no collisions at all, or the size of a table is equal to size of your universe of the keys that you are going to deal with. So, the worst case is linear, the best case is constant. Now, we know in practice that though best and worst are the cases that are not going to occur regularly. So, we look at what are called average performance, that is given a random input, how hashing is going to behave, or in particular hashing where collision is resolved by chaining. So, we try to analyze the average performance of this scheme. We want to define alpha, which is called a load factor, which basically calculates the average keys per slot. That is, if you want to store n keys and you have m slots available, then your load factor alpha is going to be n by m. So, our average performance is going to be computed using the load factor alpha, which is average keys per slot. For this analysis, we are going to assume that our scheme is of simple uniform hashing, that is any key is equally likely to hash into any one of the m slots. So, that means your input is random and your choice of m is also random. That means you take any key, the probability that it will go to any one of the slots is same, independent of where the earlier keys have been hashed to. We said such a scheme is a simple uniform hashing scheme. We will also, to make things simple, assume that the hash values can be computed in a constant time. Okay, so, you do not have a hash function which is very complicated. So, for example, we saw that if you use the division method, then you just need to compute the remainder when divided by m. So, we assume that this operation takes a constant time, and we know this is independent of the number of keys that you have in your universe. Also, easy to observe that time to search for an element depends linearly on the length of the list THK. HK is the slot where key is going to map to, and if you want to search for k, you have to search the linked list there. Right. So, your search is going to depend linearly on the size of the list THK. T is a table, HK is the slot where k is going to be mapped to, and you want to search the list there for the value k. Now, we know expected length of the linked list is going to be n by m, which is the average length of the each list. For our analysis, we consider two cases: a case where you have an unsuccessful search and a case where you have a successful search. In both these cases, we are going to analyze average performance using the load factor. So, the first result says that an unsuccessful search takes expected time theta of 1 plus alpha, that is, it takes nearly time which is proportional to the load factor. The proof is simple: any key which is not already in the table is equally likely to hash to any one of the m slots. That is the assumption on which we are working, which is simple uniform hashing. To search unsuccessfully for any key k, we need to search the end of the list whose expected length is alpha. Adding the time to compute the hash function, which is constant, the actual time required is theta of 1 plus alpha. So, it is a simple result that unsuccessful search takes expected time theta of 1 plus alpha. Now, let us look at the case of successful search. Now, probability that a list is searched is proportional to the number of elements it contains. Assuming that the elements being searched is equally likely to be in any one of the n elements in the table, the number of elements examined during a successful search for an element x is one more than the number of elements examined when the sort for element was inserted. Now, the expected length of the list to which the ith element is added is I minus 1 divided by m. So, the expected number of elements examined for a successful search can be computed using this expression. Now, one can use elementary algebra and show that this is actually bound is of order theta 1 plus alpha. The expression which captures the expected number of elements to be examined in a successful search can be simplified using algebra and shown to be of order theta 1 plus alpha. So, what we have seen is both successful search and unsuccessful search, the average performance is theta of 1 plus alpha. Alpha is a load factor of your hashing. So, if n, that is the number of keys that you want to store, is a factor of m. Like when I say n is equal to order of m, that means n is bounded by a multiple of m. So, n could be like 2m, 3m, 4m, 10m, whatever, as large as possible, but bounded by a multiple of m. So, when you say if n is of order m, we say that n is bounded by a multiple of m. In this case, the load factor is going to be like order of m divided by m, which is going to be of order of 1. Right? We know n is of order m, that would mean n is actually less than some constant multiple of m. So, n, this would mean n is actually less than or equal to some k m, and therefore, n by m we know is going to be less than or equal to k, which is nothing but a constant. So, what we observe is that if n is of order m, your searching takes constant time on average. Right? We saw that both unsuccessful search and successful search is directly proportional to alpha, the load factor. And if n is of order m, then alpha is of order 1. Therefore, on average, either a successful search or an unsuccessful search will take a constant time. Even insertions and deletions on average will take a constant time. Hence, all your operations, dictionary operations, are precisely search, and the edit operation, namely insert and delete, takes a constant time. Next, so what we have seen is, if you use hash tables and resolve collision using chaining, then on average you can search in a constant time. That means, there is a good chance that your search will happen in a constant time, whether successful or unsuccessful. Whereas, when we did searching using nonlinear data structures, our worst case was log n, and also the average cases were log n. So, hash tables on average behave much better than nonlinear data structures. The difficult part is to choose the right m, so that collisions are minimized. If you have large number of collisions, the worst case being all keys slot to the same value, then we know that that is the worst case. So, the flip side is to compute or to find an m which is going to be best, or which is going to minimize collision. That is the flip side of using hash tables, but if you have a good choice of m, then we have seen that on average your performance is going to be very efficient, which is in fact going to be like a constant and a substantial improvement over nonlinear data structures, where it was logarithmic in nature. Thank you.